Okay, hello everyone. I'm very pleased to introduce the speaker of today, Professor James Joshi. James received his PhD in electrical and computer engineering from Purdue University 2 years ago. Since then, he has been an assistant professor at Pittsburgh University. He has a lot of research interests, including, of course, security and multimedia systems. So, I'll leave the floor.
Thank you, Professor Bertino, for the introduction. And I'm very thankful to you for inviting me to give a talk here. It's like coming back to a place where it had been my home for almost 7 years. Right now, as Professor Bertino mentioned, I'm affiliated with the University of Pittsburgh and also with Laboratory of Education and Research on Security Assured Information Systems. So this is our new initiative in the University of Pittsburgh. What I'm presenting today is basically what I did as a PhD student and some of the papers that we wrote and some of the papers that are being published recently or in very near future. So it will be general overview of the different components of what we call GTRBAC, a generalized temporal RBAC role-based access control model. This research on GTRBAC was done in collaboration with Professor Elisa Bertino herself, Professor Arif Ghaffur, who was my advisor. I also have my previous lab mates, Basit Safiq and Rafai Vati, with whom I share a lot of research discussions to come up with the results that I'll present as overview. The talk is basically organized as follows. I'll briefly go through introduction and what motivated us to pursue this particular research. And I'll give an overview of the GTRBAC model. Also discuss hierarchy and separation of theory constraints, which are extension of the basic GTRBAC model. Also address some minimality and design considerations. Most of these different topics are scattered in different papers. I'll try to present as coherently as possible. We have also developed XRBAC, XML-based RBAC policy specification language to express GTRBAC policies. And lastly, I'll quickly go through related work and conclude. When we started the research, we really started trying to think what problems really are of significant importance. And we looked at various surveys, and one of the things that caught our mind was, in many surveys, you see insider attack as major threat. If you look at CSI, FBI surveys, which are often done on yearly basis or once in 2 years and so forth, it is indicated in most of the surveys that insider attack results in a lot of security breaches, pointing out the deficiencies in security management and access control solutions that employ, okay? And also, if you look at traditional discretionary and mandatory access control policies, a lot of limitations were attributed when we tried to apply those models in addressing security access control requirements of emerging applications. And we looked at many cases to see that time-constrained access is very critical to most of the applications coming up. If you further look into e-commerce security and web-based applications, many papers seem to indicate 3 basic requirements that are very much of critical importance while providing solutions that address those issues. One is tools and mechanisms which are needed to support the specification of access control policies. Secondly, most of the emerging systems have these workflow type of semantics that needs to be captured. And if you look at any workflow systems, we have the notion of task to be performed. And if you look at tasks, they are often time constrained and dependent on each other. They have separation of duty requirements. And usually tasks are associated with roles that people perform within one particular organizational context. So this generated our interest in role-based access control model, which seems to apply very well in the organizational context, where roles can be defined based on the functional requirements of any particular employee. Furthermore, if you look at e-commerce environment, secure federations of different organizations trying to achieve or provide higher level goals, services to customers. So there's a need for collaborating, sharing information, and how do you provide support for that kind of requirement? So basically we came down to what we call role-based access control modeling, and also because it has this intuitive notion of organizational functional roles, which defines what activities a particular user needs to carry out within a particular context within the organization. And I'm sure you are all familiar with role-based access control modeling. Role is basically considered as a collection of permissions, and based on that foundation, users can be assigned to roles that they need to assume to carry out particular set of activities. And we can employ constraints on different aspects of the model, users to role assignment, roles with particular permission set, and roles to role relation indicated by hierarchy to generate particular policy requirements expressed as set of constraints. And several advantages have been attributed to role-based access control model. One of the key advantages is it allows efficient security management. You can define efficient role hierarchy to capture the requirement for distributing permissions. You can define administrative roles to define what kind of security administration particular set of users can perform to decentralize administration. Role-based access control, by specifying particular set of constraints, you can enforce very efficiently principle of least privilege so that you can minimize the damage that can result from misuse of privileges. Also, a lot of the separation of duty constraint requirements that we mentioned in workflow type of environment can be expressed very efficiently, very easily by employing constraints on role-based access control model components. Furthermore, RBAC has been shown to be able to express a very diverse set of policies, making it very suitable for most of the emerging applications. And we particularly have been advocating the fact that RBAC is probably the best solution if you want to try to do collaborative information sharing environment where access control policies from different systems, different domains need to be integrated. And if you look at roles or in the role-based access control model, you can see various examples where time is of crucial importance. For example, you could have part-time staff who needs to be properly restricted to work within a particular setting in a pre-specified interval of time. You could have day doctor who must be provided all the required set of permissions to carry out his duties within the hospital in that time. You could have in financial sector auditors who are assigned for auditing jobs for a particular duration, and within that duration you need to specify set of permissions that we can allow him to exercise. So these are some examples illustrating how time is becoming a very necessary component of policy specification. And based on this, we pursued role-based access control model that has time constraint efficiently captured in it. In our GTRBAC model, basically we have triggers, we have events that indicate what state change can occur. We have triggers to capture the dependencies among events. We can specify temporal constraints, that is, we can specify what intervals or durations can a role be allowed to be available to users. When, for how long should we allow user to be assigned to a particular set of roles and so forth. And whenever user need to exercise permission, he has to activate a set of roles, and we can define for how long that activation needs to be permitted. And similarly, we have, as soon as we introduce time, associate time with roles, we have a very fine-grained semantics that needs to be captured in the role hierarchies. I'll briefly cover all these issues. So to capture event-based system, we introduced 3 states for GTRBAC. A role can be disabled, which means no user who is assigned to that particular role can activate it. So essentially, it's not available. It can be enabled, which means a user who is assigned to a particular role, which is enabled, can now exercise the permissions that are available through that role. And active indicates a role is active if a user has activated it in a session to exercise the permissions available to him through that role. And the edges indicate what are the event expressions. So enabling a role, disabling a role, and activating, deactivating, and so forth. If you look at GTRBAC model, these are the basic events which were already expressed in the diagram in the previous slide. Enabling role, enable R. You can disable a role by this command or event. Based on these event set, we have other components. First part is prioritize events. We can associate particular priority with any event. And then we also have many status predicates to capture the state of particular component of RBAC. For example, enable R to capture whether role R is enabled at that time or not. Similarly, P assign refers to whether permission P is assigned to. So based on these status predicates and simple events, we can express constraints and dependencies among various components. Trigger expressions are basically of this form. You can have number of events expressed as precondition to let some other event, for example, in this case, PRE, to take place if some other events, E1 to EN, has taken place. And you could also add status check to capture the condition which defines what next event can be allowed to occur. So, and as an example, we have enable day doctor. So if you enable day doctor role, you can enable doctor in training role after a particular duration of time. GTRBAC also allows runtime events. It can be user runtime event to indicate what activation requests a user wants to make. Similarly, it can be an administrator runtime event to enable, disable role, assign or deassign user role or role permissions, and so forth. And using these events, we actually express time constraint on various components. To express timing constraints, we use periodic time, which is of the form as shown here, I and P. P is essentially infinite set of recurring intervals. For example, you could say every Monday of this year. So Mondays are intervals that are repeating this year that we want to be associating with some particular event. And to express that, we use calendars, the usual calendars, hours, days, weeks, months, and years. An example is shown here. It indicates every week, consider days 2 through 6, and starting at the 10th hour, consider 10 hours duration. So it represents 9 a.m. to 9 p.m. of all the working days. So using this periodic time, we can express the temporal constraints on various components of GTRBAC. For example, in the first one, we're saying starting 2001, January 1st, enable day doctor in daytime. So daytime is a shortcut expression for the one we saw in the previous slide. The next one indicates starting 2000 on Mondays and Wednesdays, assign particular Dr. Smith to the day doctor role. Similarly, you can express duration constraint where you indicate how long particular event is allowed to be valid. For example, you have 5 hours enabled the doctor in training, which indicates that the doctor in training role needs to be allowed only for, enabled only for 5 hours. But when you specify duration constraint, you need to have an associated trigger to enable, actually enable the doctor in training role. So in the next one, you see activate day doctor for Smith enables doctor in training after 1 hour. So if Dr. Smith activates day doctor, then doctor in training is enabled, but because of the duration constraint, it is enabled only for 5 hours. So these are some example of constraint, temporal constraint that we can specify on various components of GTRBAC. We can also specify many different constraints on activation state of a role. For example, we could say a role should be allowed to be active only for a particular duration. You could have a more specific constraint, for example, per user role. Given a user and a role, the activation duration should be restricted to DU active. So these are just 2 examples. We have other set of activation time constraint that can be expressed. So here's a more full-fledged example where we have a healthcare system. You enable day doctor role in daytime, night doctor role nighttime. And if you look at constraint 2B, we are saying there's a constraint that nurse in training should be enabled only for 2 hours in a period, in a duration of 6 hours. And in the next one, constraint 3A, we enable C1, the constraint is actually enabled. So once C1 is enabled, in the period of, in the duration, within the duration of 6 hours, nurse in training can be enabled for 2 hours. So this is a simple example illustrating the use of GTRBAC constraints. Here's another example that we could use GTRBAC for subscription-based system. This is overly simplified. If you have a video database used for video on demand, and if you have subscription-based access to the resources videos, then you can use activation time constraint on roles MB1, MB2, and MB3 to limit the access based on how much you are paying for the video on demand. So these are some basically overview of some of the constraints that can be expressed in GTRBAC. And since it has many constraints, obviously the issue of conflict and ambiguous semantics is crucial. In particular, GTRBAC can have 2 anomalous situations. First, we could have simultaneous occurrence of conflicting events. For example, at the same time, enable role, particular role, R, can occur with another event which is trying to disable the same role. Similarly, we could have arbitrary triggering of triggers based on events that are validated at particular time, generating ambiguous semantics. We'll look at a simple example. And to take care of these cases, we have conflict resolution rules. Basically, we use higher priority text precedence, disabling event or negative text precedence when there are same priority opposing events. For example, disable R takes precedence over enable R if they have the same priority. And also, since we have activation time constraint, enabling time constraint, we use more specific constraint to override the less specific constraint. So to capture these two anomalous situations, we have a event dependency analysis that actually tries to find out set of triggers that may give very ambiguous semantics. And having removed that ensures good behavior on the execution of the model. And at runtime, we could still have a need to resolve conflict when events of opposing nature occur at the same time. And we use primarily priority-based conflict resolution. And we have categorized three types of conflicts in GTRBAC. Type 1 is essentially between events of same type but of opposing nature. So enable R and disable R are events trying to address the same issue, but they have different opposing effect. So if they both occur at the same time, we basically use priority to resolve. Type 2, there could be cases where dissimilar types of events, but somehow they oppose each other. For example, if there is an activation request to activate role R for you, and at the same time there is another event deassign R for you, we want to be able to resolve this case because you can't grant both the event request. And type 3, we could have constraint specifications that are themselves conflicting. For example, we could have two duration constraints where duration specification might be different for the same event, or you have different durations, but the opposing events are specified. And similarly, we could have per role specification, which is more specific, per user roles specification, which is more specific than per role specification. So here we simply use more specific overrides the less specific case. So as I already mentioned, type 1 conflicts we simply resolve by using priority, text precedence rule, and if we have this same priority on the opposing events, we do the disabling event text precedence. For type 2, activation event has lower precedence. Basically, type 2 event conflicts occur when you have an activation related event and another non-activation related event trying to occur at the same time, but they have opposing effect. So we give less priority to activation event because, for example, if a role is disabled, we should not be able to activate it. Type 3B, it's, as I have already mentioned, more specific specification text overrides the less specific. So per user role is really more specific because it says given a user and that particular role, the constraint is this. But per role is only for given that role, the constraint is as pre-specified. So here's an example. If you have this set of events trying to occur at the same time, then based on this resolution, some of the events need to be discarded. And I mentioned about triggers creating ambiguous semantics. If you look at this example, we have two triggers. First one, enable R1, enables or disables R2. If you have enable R2 event occurring, then disable R1 events should also occur. And if you assume that at runtime you have these two requests generated, enable R1 and enable R2, depending on which one you take first, you have two different set of events selected for firing. For example, if you take enable R1 first, it fires TR1. That means disable R2 will also be an event that needs to be fired, which means TR2 cannot fire because disable R2 is already there, and TR2 starts with enable R2. Similarly, if you take enable R2 first from the runtime request set, then you fire TR2, trigger TR2 first, and include disable R1, which is on the right side of the trigger. But once you do that, you cannot fire TR1. So based on which one fires first, which you chose, you have two different set of events, valid events you can compose. So we want to avoid that because that's ambiguous given a particular request and particular trigger set. It has multiple paths, and we want to be unambiguous in such situation. And to avoid such situation, we employ level dependency graph technique to detect the ambiguity. And if you look at, we have an algorithm. If you look at the previous example with TR1 and TR2, it essentially generates, based on this algorithm, this directed graph with labels plus and minus. And by using analysis of this directed graph to find some cycles which have particular labels, we could identify those trigger set which can possibly generate ambiguous semantics. So the result basically is, if you have a set of triggers, we can say it is safe if the level dependency graph has no cycle with particular label. And it can be computed, the cycles can be detected in polynomial time. Now let's quickly overview role hierarchy. We needed to revisit role hierarchy because now we have roles with time constraint, and once roles have temporal duration, how two roles which are related through hierarchical relation changes the inheritance semantics. So if you remember, role hierarchy is there basically to allow a senior role to inherit permissions that junior roles have. But since senior and junior roles can themselves have different time intervals associated with them in which they can be enabled or disabled, the semantics can change significantly. So we looked at this issue. Basically, temporal role hierarchies, we tried to capture all the fine-grained semantics that can be introduced by having time constraint by separating the permission inheritance and role activation inheritance semantics. We'll quickly look at that. And also, this separation allows capturing the effects of the presence of temporal constraints in a much more fine-grained way. The separation basically gives us three different types of hierarchy. The first one is I hierarchy, which is simply a hierarchically related roles where senior inherits junior's permissions, but user who is assigned to a senior does not automatically cannot activate the junior roles. He can inherit the permission but cannot activate the junior roles. Role activation hierarchy is the dual of I hierarchy. Here, senior does not inherit junior's permissions, but anyone who is assigned to the senior can activate the junior. So he can, in effect, use the permissions that are available through juniors, but he has to actually activate that. So it has implications in cases where you use auditing system to determine accountability and so forth. And one other advantage with this kind of separation is you can specify separation of duty constraints on roles which may be hierarchically related, which was not possible when we employed single hierarchical semantics, which is actually the semantics given in the last one, IA hierarchy, which is the most common. If you look at standard RBAC model, that's the semantics employed. That is, senior inherits junior's permission. A user who is assigned to the senior can also activate juniors. Now, we talked about the different semantics that can arise. If you look at this diagram, you have software engineer role and programmer role, assuming that software engineer role is senior of programmer role, and P sub P is the permission set that is available through programmer role. Assuming that blue line interval indicates the time when the senior is enabled, and red indicating the time when the junior is enabled. So we have cases where we have tau 1 and tau 2. How do we attribute the semantics of inheritance between these two roles? And to capture this, we introduce strongly restricted and weakly restricted temporal role hierarchies. In strongly restricted case, we allow inheritance to occur only when both the roles are enabled. So in tau 1, if you have inheritance hierarchy, the strongly restricted inheritance hierarchy denoted by IS, a user assigned to the senior role SE is not authorized for permission PP in the interval tau 1 where only the junior role was enabled. Similarly, if you look at activation hierarchy, it applies to the second case, that is, a user who is assigned to the senior role cannot activate a junior role in tau 2 because junior role is disabled, although senior role is enabled. So this is much more fine-grained semantics that we were able to capture. Similarly, if you look at weakly restricted, we do allow inheritance even though both the roles are not enabled at the same time. For example, if you look at I hierarchy, where permission inheritance is allowed, a user assigned to senior role is actually, I believe it's a typo, is actually authorized for PP in tau 2. Oh, that's fine. If you consider inheritance with weakly restricted semantics, this should have been actually not his typo there. Even when both the roles are not enabled, you do allow inheritance. So even in tau 2, where the junior role was not enabled, you allow permission of the junior role, however, to be used by the senior role. And similarly, in activation hierarchy, a user assigned to the senior role can activate, even if the senior role is disabled, the junior role. So by virtue of it being assigned to a role, even though that role is disabled, the junior role is available to the senior role. And what's the usefulness of this different sets of hierarchies? Here's one example. If you have day doctor role and night doctor role, and if you want to be able to have a part-time doctor role which can be a role that overlaps the two intervals like daytime and nighttime, you can efficiently represent this as a policy. If you look at the part-time doctor role, you have those greenish intervals indicated there. And The red indicates the day doctor role from 9 a.m. to 9 p.m. and so forth. So if you have strongly restricted inheritance hierarchy, and if you have a part-time doctor role, which is enabled from 3 p.m. to 6 p.m. and 7 a.m. to 10 a.m., you can easily capture this requirement, because by virtue of the inheritance being strongly restricted, if you look at 7 a.m. to 10 a.m., that interval for part-time doctor overlaps with day doctor and night doctor. So it automatically can retrieve the day doctor as well as night doctor role in the two sub-intervals. So you can have this high-level policy easily implemented in hierarchy. Also, we have a very long list of separation of duty constraints that can be expressed to capture different requirements. Actually, we have grouped that into these 6 categories: role enabling SODs. For example, you could say a particular group of role, from a particular group of role, maybe you want to make sure that node 2 is enabled at the same time or disabled at the same time. So that addresses both availability as well as restrictive constraint. Similarly, you can have user role assignment SODs saying particular user cannot be assigned to 2 different roles. And the other SODs that we can capture in GTRBAC include role permission, activation time SODs, and also what we call possibilistic role activation or permission acquisition. So briefly on these 2, possibilistic activation is needed when you have hierarchy structures. Actually, these 2 are needed for I and A hierarchy structure in presence of I and A hierarchies. So possibilistic activation, it is dealing with who can activate which role. So it captures implicit as well as explicit assignments. Implicit means by virtue of a user being assigned to a senior role, he can activate a junior role. But you want to be able to capture that within a constraint. And possibilistic is the permission assignment aspect, while possibilistic activation was user assignment aspect. So if you look at this example, a user in particular user set cannot acquire different permissions in P at the same time. So by using first order logic, we could express these constraints, which are essentially separation of duty constraints. And also we can say no, for example, no 2 users in particular user set can acquire permission in a given set. And we also employ time constraint, the notion of time with the SODs, and it's more intuitive. If you look at different forms of time, if you attribute SODs with intervals or periodic time expressions that we use in temporal constraint, we get 3 different forms of different strength that we can specify. For example, if you have this expression IP UAS, you are indicating a user assignment constraint. For example, a user in particular user set cannot be assigned to 2 roles in particular role set. If you have this, you are associating set of intervals indicated by IP, which is periodic time expression as we use in the earlier constraint forms. That can be attributed to 3 different forms of semantics. The weak form is at any instant in that particular set of intervals, if a user is assigned to a particular role in R, at that instant he cannot be assigned to another role. So we're not saying that he cannot be assigned to another role within the same role set at another time instant. It's only concurrent assignment that is not allowed. Strong form is if you have IP, which is basically a recurring set of intervals, we're saying that if there is an instant in which a user is assigned to a role, for no other instant in that interval, he can be assigned to another role in that particular role set. So it applies to the whole interval, each of the intervals in IP. Still more form is extended strong form, that is, if a user has been assigned to a particular role at no time instant at all throughout the set of intervals in IP, he can be assigned to another role. Okay, I guess I have to fast forward. We also address minimality and design consideration. Basically, the purpose is we have introduced so many constraints so that we could capture very fine-grained policy specification. And is it really useful? So the issue we addressed was, is there a minimal model that can express the same policies that the full set of constraints can be used to model? And that brings in the issue of clarity of semantics versus complexity of specification, essentially usability aspect of the model. And we try to address this by trying to do some complexity analysis in terms of how many roles are needed, how many assignments are needed, how many temporal constraints are to be handled, because handling temporal constraint is a significant task, and what is the hierarchy, complexity of hierarchy structure, because that also adds some processing time. And we use this notion of activity equivalence. If C1 and C2 are two configurations, which has user set, role set, permission set, and role hierarchy as defined, as well as a set of constraints to enforce particular policy, you could represent the same thing in two different configurations of this tuple. That is, you have C1 and C2. They are said to be A equivalent if a particular user can acquire a particular permission in C1 if and only if he can do the same thing in another configuration. So they are essentially equivalent. And by using this notion, we have created this family of A equivalent models where GTRBAC 2 represents the basic, the complete set of constraints that we can specify. And at level 1, we remove one particular type of constraint. And level 0 is basically we have constraint only on role enabling. We don't have temporal constraint on assignments of user to role and role to permission and so forth. And we see that there are alternative representation because of A equivalence relations among different configurations that we can employ. And they have trade-offs in terms of how many roles are needed and so forth. So essentially, here's a quick example. If you have the first one on the left top, it specifies temporal constraint on user to role assignment. You can express the same thing by transferring the temporal constraint on roles, but you are creating more roles, but you are avoiding user to role assignment constraints. And similarly, you can have another alternative representation where you create, based on those temporal periodic time expression, distinct set of expressions shown here, P triple dash and so forth, which are disjoint. So roles here on the third diagram is having enabling time periodic temporal constraints which are distinct from each other. So these have different trade-offs based on the figures, the different parameters that we saw. So this is just to point out that with some attributes like time introduced, it's a significant issue when it comes to usability. So I guess I'll forward to, we also have XML RBAC specification language developed, and it can specify almost all of the constraints that we have we can express using GTRBAC model. And here's a snapshot of XML policy sheet, the high-level view, which has different components that can be employed. we have a architecture which is actually mainly to be attributed to Rafay Bhatti, who is also I have been working with. He was mainly responsible for implementing this architecture. So I'll move to conclusion. Basically, we have role-based access control model, which is able to support very diverse set of access control policies. Time is a crucial requirement with that we try to capture in and develop GTRBAC model. So I think I can stop here. If you have questions, you can ask now.
How is the implementation of that going?
Implementation going?
Yes,
Yeah, we have implemented a prototype already. And one part we haven't included in this implementation is the complete set of SOD constraints. Because I just mentioned 6 categories, but each category has different number of constraints that you can express. So altogether, I think we have about 36 SOD constraint specification, which is a substantial work to implement. And that is one of the reasons we try to address the issue of expressiveness minimality. Can we have a smaller set of constraints to express everything?
Okay.
Well, thank you very much.
Good job.
Yeah.
I guess you had a few